welcome to the deep dive. There's so much exciting talk these days about renewables, solar, wind,
It's definitely front and center.
and yeah, for good reason, it's vital for the future. But before we fully get there, I think it's really important to understand the foundation. The bedrock our whole modern world's been built on since the Industrial Revolution.
Fossil fuels.
Exactly, fossil fuel. They've been the powerhouse, sort of quietly running everything for, well, centuries now.
It's true. I mean, think about it. Ancient civilizations, they ran on renewables, sure, but the scale of our world, that's down to fossil fuels.
Absolutely. And that's kind of our mission today, to unpack that story. We're going on a journey, right?
Yes.
From their ancient origins, deep underground,
Yeah.
to how we actually get them out, and then how they're turned into just countless things. Fuel, materials, everything. It feels like essential background.
It really is. And for this deep dive, we're drawing on insights from experts who walk us through it all. We'll look at the upstream first, how it forms, how we find it, get it out. And then the downstream, the refineries, and it's surprisingly complex, way more than just drilling a hole and hoping for the best.
Sounds like quite the trip. Okay, let's start way back. Millions of years ago.
Yeah,
Deep inside the Earth. Hydrocarbons. Oil and gas.
yeah.
We picture black goo, right? But where does it actually come from? It's organic, carbon, hydrogen.
Precisely. The origin story is pretty amazing, actually. It's basically ancient biological stuff. Tiny marine plants, animals, millions, even hundreds of millions of years ago.
Wow.
They lived, they died, sank to the bottom of shallow seas. And over these huge timescales, maybe 150 million years back, the conditions were just right. This organic matter mixed with sediment, layer upon layer, eventually forming what geologists call the source rock. Usually a thick black shale, maybe about 5% organic stuff in it.
Okay, so source rock. Then geology takes over. More sediment piles on, pressure, temperature, like a slow cooker.
That's a perfect analogy. Yeah, the Earth's own slow cooker, basically, with no oxygen. So around 50, maybe 60 degrees Celsius, that organic material turns into this waxy stuff called kerogen.
Kerogen.
Right. Now, here's where it gets really specific. Crank the heat up, say 90 degrees Celsius. That kerogen transforms into crude oil. Get it even hotter, like 150 Celsius, and you get natural gas. It's a surprisingly narrow window, those specific temperatures and pressures for each one.
That's incredible. The Earth literally cooking oil and gas from old life.
Yeah.
But okay, once it's cooked, how does it end up in those pockets we can actually drill into? It doesn't just stay in the shale, does it?
That's a really important point. No, usually it doesn't. See, oil and gas, they're less dense than the water that's naturally filling the pores in the surrounding rock.
Oh,
so they naturally want to float upwards. They migrate, moving through porous rocks, sandstone, limestone, things like that.
Like rocky sponges.
Exactly like rocky sponges. They keep moving up until, bang, they hit something they can't pass through. An impermeable layer, a cap rock.
Right. Now, if the geology's just right, if it forms a sort of arch shape, what we call an anticline, like an upside-down bowl that creates a trap.
Oh, okay.
And the oil and gas collects in the porous reservoir rocks underneath that cap rock. These traps are absolutely crucial. Without them, the oil and gas would just keep going, seep out at the surface, form tar pits, or just disappear over time.
So that's why those ancient seabeds are key, because they have the right layers.
That's a big part of it. Something like 60 to 70% of today's oil production is offshore, from areas that were once ancient seas.
Okay, so you need the source rock, the right cooking conditions, a path to migrate, and that perfect geological trap.
Yeah.
Finding these hidden pockets, that must be a massive challenge. How do they even start?
Oh, it's a huge undertaking. The whole exploration and production, EMP, it's incredibly complex, incredibly expensive. It starts with geological surveys. Geologists look at surface rocks, trying to get clues about what's underneath.
But the real heavy lifting comes from geophysical surveys, usually seismic. This is where they generate sound waves, maybe controlled explosions on land or special air guns from ships at sea. And then they listen for the echoes bouncing back using sensors, geophones. It's basically like creating an ultrasound map of the Earth's layers to spot those potential traps. Just this survey part can take years.
Years. Just mapping. Wow. And then, if they find something promising, comes the drilling. That sounds tricky too.
Absolutely. Drilling is super precise, very costly, often around 30% of the total well cost. And just getting to the point where you can drill might take several more years after the surveys.
And the cost.
Huge. Even a fairly shallow onshore well, maybe $1 to $2 million US, 1 to 2 crores in India. Offshore wells, significantly more. It's a massive investment.
That is a huge gamble. You can spend all that time, all that money, and just drill a dry hole.
You absolutely could. It's definitely a high risk, high reward. Now, if they do hit oil or gas, the initial production, it often relies on the reservoir's own natural pressure. We call it self-flow.
Okay.
But that usually only gets you maybe 20–30% of the oil in place.
Only that much.
Yeah. So to get more out, they need artificial lift. That might be those nodding donkey pumps, sucker rod pumps you sometimes see in fields.
Right.
And then there are even more advanced, enhanced recovery methods, things like injecting steam, CO2, or water back into the reservoir to kind of push more oil towards the well. These can boost recovery by maybe another 40 or 50%.
So definitely not just drill and pump. It's a long technical game. And you mentioned costs, but what are some other big challenges in this upstream part?
Oh, plenty. Yeah. A huge one is managing the water that comes up with the oil and gas. It always does. We call it produced water.
Right.
And it's not just water. It's often really salty. It's got traces of oil still in it, dissolved solids, even naturally occurring radioactive materials. Whoa.
Radioactive? Yeah, naturally occurring. Usually very low levels, but certain elements in the rocks dissolve into the water over time. It has to be managed carefully. And you can't just dump this produced water, partly because the salt causes scale that can choke pipelines, but also because there are really strict environmental rules. Like offshore, you need less than 40 parts per million of oil in the water before disposal. Onshore, it's even stricter, maybe less than 10 ppm. Treating this water is a major operation itself.
Okay. And the oil-water mix, that sounds tricky too. Emulsions.
Exactly. They form these stubborn emulsions, so you need special chemicals, de-emulsifiers, plus heat, pressure, sometimes even high-voltage electricity to break them apart and separate the oil and water properly.
And the oil and gas itself does it vary a lot from place to place.
Oh, definitely. Natural gas, for example, the methane content might be 70%, might be 90%. You can have other hydrocarbons too, ethane, propane, butane. And impurities like hydrogen sulfide, H2S, or carbon dioxide.
H2S, right.
And crude oil. It's a super complex mix. Besides hydrocarbons, it's got compounds with nitrogen, sulfur, oxygen. We talk about sour crude if it has a lot of H2S or sulfur.
Sure.
And sweet crude if it has very little. That sulfur content really matters for refining. Another key thing is API gravity.
API gravity.
Yeah, it's basically a measure of how light or heavy the crude is. Light crude has a higher API gravity, over 31. Heavy crude is under 22. It's a big factor in pricing because lighter crudes are generally easier, cheaper to refine into valuable things like gasoline.
I see. So besides water management and varying quality, what other big picture challenges face the upstream guys?
Well, maintaining that crude quality consistently is tough. Fighting corrosion in all the pipes and equipment is constant. Preventing scale buildup, ensuring safety, obviously huge priority. Managing environmental risks, and of course, just the sheer scale of investment needed.
Yeah.
These projects need massive capital. That's often why you see big state-owned companies playing such a dominant role. Like in India, ONGC produces something like 80% of the country's domestic oil and gas.
ONGC, right. And the global scale. It's just mind-boggling when you think about it.
It really is. Globally, something like 43,000 oil and gas fields across maybe 500 to 75 sedimentary basins. But here's the kicker. Only about 215 of those basins are actually producing.
Wow.
And get this, 90% of all the oil and gas comes from just 10% of those productive basins.
No kidding.
Yeah, that extreme concentration really underlines the whole geopolitics of energy, doesn't it? And even with all that, there are still huge potential frontiers, like the Arctic, that are largely untapped.
Okay, so that's the upstream journey, finding it, getting it out, initial cleanup. But like you said, that's only half the story. You get this raw crude oil. You can't put that in your car, right? Or make plastics from it. What happens next?
Exactly. That's where we shift to the downstream side, the refinery.
Refinery. Okay, when I hear refinery, I think petrol, diesel. But you're saying it's more than just fuel.
Oh, absolutely. Fuels, petrol, diesel, jet fuel, kerosene, heating oil. That's a huge part, yes.
Yeah.
But refineries are also gigantic chemical plants. They produce petrochemicals.
Petrochemicals.
Yeah, the basic building blocks for so many things we use every day. Plastics, synthetic fibers, solvents, fertilizers like acetic acid, ethylene, a whole range. Plus, they make lubricants for engines, asphalt for roads, petroleum coke for steelmaking. It's vast. And what's interesting is that different refineries aren't all the same. They're often optimized, to make more of certain products based on what the market needs and what kind of crude oil they're getting. Not a one-size-fits-all deal.
Okay, so this complex mix arrives at the refinery gate.
Yeah.
What's job number one? The very first thing they do.
The absolute first critical step is desalting. Even after some upstream cleanup, crude oil almost always has some water mixed in
Yeah.
and dissolved salts. These salts are terrible news inside a refinery. They cause really bad corrosion and they foul up equipment, especially heat exchangers.
Foul up, like clog them, build up gunk.
Exactly. Scale buildup, deposits, it just kills efficiency. It can cause expensive damage. So they have to break those stubborn water oil emulsions. They use special chemicals, demulsifiers, add heat, pressure, sometimes even zap it with high voltage electricity to separate the water and salt out.
Sounds pretty intense for just desalting.
It might seem minor, but honestly, desalting can be the bottleneck for the entire refinery. If that unit isn't running well, it slows everything else down. Huge financial impact.
Got it. Critical first step. So once it's desalted, then we get to those big towers you always see, the distillation.
That's right. Now you're at the heart of the refinery, the crude distillation unit, or CDU. This is where the first big separation happens, basically sorting the crude oil components by their boiling points. It runs at atmospheric pressure.
How does it work?
Okay, so you heat the crude oil in a furnace, often mixing in some steam, and then feed it into the bottom of this tall column, the fractionating column. As the hot vapor rises up the column, it cools down. Different components condense back into liquid at different temperatures on trays or packing inside the column. The latest stuff like naphtha, fewer carbon atoms used for gasoline or chemicals, has the lowest boiling point, so it goes all the way to the top.
Okay.
Heavier things condense lower down, so you draw off different streams or cuts from side outlets at various heights. You'll get kerosene for jet fuel, then diesel, then heavier gas oils, all coming off at progressively lower points, higher boiling points.
And the stuff left at the very bottom, the really thick, heavy gunk that doesn't boil off.
Exactly. That's the atmospheric residue. Thick, heavy, often has metals in it. That doesn't just get thrown away, though. It gets processed further, maybe in a vacuum distillation unit, to make things like lubricating oils, waxes, asphalt for roads, bitumen, and petroleum coke.
Okay.
And one other really key process, often happens later, is blending. Taking all these different streams you've separated and mixing them very precisely to meet the exact specifications for the final products, like different grades of gasoline or diesel that works better in winter versus summer.
It's already sounding way more complicated than just boiling oil. I think you mentioned earlier a refinery might have something like 22 different operations. How do we even wrap our heads around that?
Yeah, it's definitely not just one or two towers. It's a whole interconnected city, really. But we can simplify it. Think of refineries as having maybe 4 main functional blocks, like different districts.
Okay, 4 blocks. What's the first?
First is the separation block. This is things like the CDU we just talked about, vacuum distillation units, maybe naphtha splitters. They all do purely physical separation, mostly based on boiling point or how volatile things are, just sorting.
Okay, sorting. Block number 2.
Second is the treating block. This is all about purification. Desalting fits here. But a really crucial part is hydrotreating. See, crude oil has sulfur and nitrogen compounds, pollutants, and they can poison catalysts later on.
Right.
So hydrotreating uses hydrogen gas under pressure with a catalyst to react with those compounds. It turns sulfur into hydrogen sulfide, H2S, and nitrogen into ammonia, NH3. This step uses a lot of hydrogen, and then, of course, you have to deal with the H2S and ammonia produced.
Okay, so separation, then treating, purification. What's next?
Third is the reactive transformation block. This is where the real chemistry magic happens. You're actually changing the molecules. Think cracking, either using heat, thermal, or catalysts to break down big, heavy, low-value molecules into smaller, more valuable ones, like components for gasoline.
Oh, breaking them down.
Yeah, and other processes like alkylation, isomerization, reforming. These are all chemical reactions designed to rearrange molecules or combine them to upgrade lower value streams into higher value products, like boosting the octane rating of gasoline.
So breaking, rearranging, upgrading. And the 4th block.
The fourth is more about physical operations, less about chemical change, more about allocation. Blending, which we mentioned, fits here. Also things like maybe a kerosene splitter or a butane splitter units that might just divide a stream based on weight or volume for different uses or markets.
Separation, treating, reaction, physical operations. It really is like a mini city, isn't it? Each part doing its job. And given the stuff you're handling, safety must just be paramount.
It's number one, always, non-negotiable. And it relies on really understanding the properties of these materials. For example, flashpoint. That's the lowest temperature where a liquid gives off enough vapor to just momentarily ignite flash if there's a spark.
Okay, flash point.
Then there's the fire point, slightly higher temp, where it'll actually keep burning for at least 5 seconds. These dictate how you handle and store things safely.
Right. What else is key for safety?
You absolutely have to know the flammability limits. The lower flammability limit, LFL, that's the minimum concentration of vapor in air you need for it to ignite. Below that, it's too lean, not enough fuel, won't burn. The upper flammability limit, UFL, is the maximum concentration. Above that, there's too much fuel, not enough oxygen, it's too rich, won't burn either. You must operate outside that flammable range between the LFL and UFL.
Okay, stay out of the danger zone.
Exactly. And finally, auto-ignition temperature. That's the temperature where a substance just bursts into flames on its own without any spark or flame needed. Understanding all these concepts is just fundamental for designing safe processes, safe procedures, everything.
Yeah, that really drives home the risks and the precision needed. We've covered a lot on oil and gas, but hang on, what about coal? It's a fossil fuel too, right?
That's a great question. Yeah, absolutely. Coal's another major player. Its origin is a bit different, though. It comes mainly from the remains of plant matter. Think ancient swamps.
Okay, swamps, not seas.
Right. But the overall processes, burial, pressure, heat over millions of years, they're similar in principle to oil and gas.
Yeah.
It's just the starting material, land plants versus marine organisms, and the specific geological conditions that determine whether you end up with coal, oil, or gas.
So the cooking process is different.
Well, the process for coal is called coalification. It involves increasing the carbon content, often through something called demethanation, basically. Methane gas gets squeezed out as the plant matter transforms into peat, then lignite, bituminous coal, and finally anthracite.
Is that methane related to coal bed methane?
Exactly. That methane gets trapped within the layers, the seams of the coal itself, along with some other gases produced during that coalification process. So yeah, you could say the Earth is busy cooking up oil, gas, and coal from all sorts of ancient life.
It's just an incredible journey we've traced
Mm-hmm.
from like ancient muck on the seabed
Mm-hmm.
through these immense geological forces, high-tech searches, complex extraction, and then into these refinery cities making everything from fuel to, well, fertilizer. It really shows why even with the push for renewables, these fossil fuels are still so deeply woven into everything.
It really does. That's definitely a key takeaway. I mean, renewables are advancing fast, which is great, but even optimistic forecasts suggest maybe 30 to 50% of global energy from renewables by 2050.
Still leaves a big chunk for fossil fuels.
Exactly. It means oil and gas are going to be crucial for decades to come, especially for energy security in places like India, importing over 80% of its oil. That's a massive economic factor.
And the industry itself isn't just sitting back, is it? You hear about new tech, unconventional resources.
Oh, absolutely.
Mm.
The focus is definitely shifting more towards these harder to get resources. Shale gas, which needs fracking.
Right.
Gas hydrates these huge kind of ice-like methane deposits, mostly under the seabed. Huge potential there, but tricky. Coal bed methane, which we just touched on, and oil sands.
Oil sands, like in Canada?
Yeah, Alberta, Canada. Those oil sands hold maybe half the world's proven oil reserves,
Yeah.
believe it or not. But getting that thick bitumen out of the sand, it's complex, uses a lot of energy. Generally, all these unconventional sources are tougher, more expensive to produce than the traditional stuff.
So technology is key to unlocking those.
It's the game changer, all across the board, really. AI helping analyze seismic data, augmented reality helping crews in the field, better ways to visualize the reservoirs, and things like horizontal drilling. That was revolutionary back in the 90s.
Horizontal drilling.
Yeah, instead of just drilling straight down, they learned how to steer the drill bit sideways, horizontally, through the reservoir rock. Means you can access way more oil from just one drilling pad. Huge difference.
Wow.
And it's not just about finding more oil and gas anymore. Even the big traditional players like ONGC, they're diversifying, looking into things like underground coal gasification, pushing harder on CBM and gas hydrates, even exploring green hydrogen. The industry is constantly adapting, evolving.
It really is a dynamic picture.
Yeah.
We've covered so much today, from deep earth geology to the complex chemistry turning raw materials into the fuels and chemicals literally powering our lives.
Mm-hmm.
It really hits home that fossil fuels aren't just, commodities we dig up.
Mm-hmm.
They're products of these incredible natural forces and a whole lot of human ingenuity.
That's a really good way to sum it up. It is this constant interplay, isn't it, between what the Earth provides and our technology, our understanding, to find it, get it, and transform it. It really makes you think.
Yeah.
As we transition, hopefully, towards a more sustainable energy future, What are the next big challenges, the next innovations?
Hmm.
How's this whole energy story going to keep unfolding?
That's a great question to end on.
Mm.
Well, we hope this deep dive has given you a richer picture of the energy foundation we're all standing on right now. Keep questioning, keep exploring. Thanks for joining us on the deep dive.